the recording right here. This is the paper two discussion class for the 970 to AS class. Question number 1. Okay, question number 1 is a pretty good one. Let's have a look at this question. Have a look, everyone. Figure 2.1 shows the variation of distance x along a wave of its displacement d at a particular time. The wave is a progressive wave and has a speed of 330 meters per second. Use figure 2.1 to determine the wavelength of the wave, which is pretty simple. We can see it from the graph. The wavelength is 0.6 meter. You just write it over here. Hence, calculate the frequency of the wave. So you go for v equals to f lambda. Here is your v, here is your lambda. You find and calculate the f. That's pretty simple. 3 marks. So there is 1 mark and 2 mark, total 3 marks. Number B is interesting. Have a look. A second wave that has the same frequency and speed as the wave shown in figure 2.1, but has double the intensity. The phase difference between the two waves is 180 degrees. On the x-axis of figure 2.1, sketch a graph to show the variation with distance x of the displacement d of the second wave. So first of all, it says the phase difference is 180 degrees, which means these two waves are going to have reversed crests and troughs. So in places where this wave has crests, the second wave will have troughs and vice versa. That's point 1. Point 2 is that it says it has doubled the intensity, whereas on our graph we are plotting the displacement, or for maximum displacement over here can be referred to as the amplitude. So for the second wave we need to figure out how much will be the amplitude. It wouldn't be double, because intensity is double doesn't necessarily mean amplitude is double. So we have to find out how much of the amplitude is gonna be. So let's copy this up and let me show you how to attempt this. One of the things that we can apply for our convenience over here, actually this is how you're supposed to do this, is that we know that intensity of any wave is given by this relationship, I proportional to amplitude squared. So if I just now subject the amplitude squared, I get I is proportional to a square proportional to I, or a is proportional to root over of I. This is the important bit. The reason I'm subjecting the amplitude over here, because I want to find out how the change of intensity affects the amplitude. So in this case, you can see that A is affected by the root over factor of I, which means whenever I has been increased to 2I, the A should be affected by a factor of root over 2A, because on top of the I, we have the root over sign. So double the intensity will give you root 2 times the original amplitude. So that's one way to approach it. So in this case, we have to draw a second wave, which is going to have root 2 times the amplitude of this wave. Now I have a look over here. On the y-axis, we don't have any division mark. We don't have any scale, but we have divisions. And you can see that the given wave has has an amplitude of 5 divisions. So if we try that for the new amplitude, let's say I'm going to write any. You don't have to write these stuffs as long as you understand that. So you can find this out by root 2 into 1, root 2 into 5 division, and this should give you 7. Pretty close to 7, because root 2 is about 1.41 something. So we're gonna try to draw a wave over here, which would have a amplitude of 7 divisions and have perfectly opposite phase of this particle. So I'm gonna, for the sake of easier drawing, I'm gonna first label those points so that you can draw them freehand, and then we will. I'm gonna show you how to continue these things. You can. So I'm gonna first label those points where the wave is supposed to go through. So this point is perfectly all right, in my opinion. This is okay. And then this is where, I mean, have a look at this location. This is actually the halfway point of this 5 division box, or I can say that this is exactly at the midpoint of these 5 boxes. So I'm going to go vertically down along this point, and I'm going to find out the 7th division and give a mark over here. This is going to be my trough for my wave. And then on this side, this is going to be the crest, so this is also going to be on the 7th division. So, and I'm definitely going to have the cross points at the cross points. So try to understand this part of the wave, which, because the rest of the part will be exactly identical to this one. It's a continuation. So because the wave is 180 degree out of phase, so the crests become crests. So the crests become troughs, and the troughs have to down as crests. And also the amplitude is increased to 7 division because the amplitude intensity is doubled. So I'm going to try to draw a wave of this shape here as best as I can. I hope I can do that. So one part is up to here, and the other part, oh, this is difficult. I have to lower it a lot more than that. আচ্ছা আমি খালি হাতে আঁকে, এটা আসলে কার্ভ দিয়ে আঁকা ডিফিকাল্ট হচ্ছে। So I'm going to try and draw this freehand. So this should go like this, and then this should rise up, pass through here, and go up like this, and this can go down right here, and you have to complete the rest of the graph as well, which I'm leaving in your hands. One of the things that you can always do, just to convince the examiner that you know your stuff, because the quality of the drawing of this wave is somewhat arbitrary because you're supposed to draw freehand. But as long as you label these points, let's say if I label this point as with a dot circle, the examiners will know for a fact that you know how to do the calculation. And this part of the calculation that I just did over here, that this part that well, আচ্ছা এখানেই তো no এখানে yeah, this part of the calculation that I just did over here, that amplitude is supposed to be root 2 times the root over a. You don't essentially have to show this calculation, but if you want to keep this calculation, you can always keep them beside the graph, sort of like a rough working. The examiners don't need it because they're going to only mark you on this point. But if you have this calculation over here, which you don't rub off, the examiners will understand that you really know how you did the math. So that can be an added advantage. It's not essential, but you can keep those calculation on the right side, because essentially for this question there is no allowed space or given space to show you the calculation. So they'll be only marking you on the variation of the wave, so how you have drawn the wave. So and you have to also obviously complete the whole wave. So I think that makes sense. And let's look at the question number 2. Question number 2 is actually pretty simple. You have already seen this thing in action. We have a little bit of n correction over here, so that's why we do not use lambda by 4. We use we use the L2 minus L1 equals to lambda by 2. So this distance over here is going to work as a lambda by 2. And in this case, I believe they have asked us to draw the stationary wave. Yes, this is the important bit. On figure 6.1, sketch the form of the stationary wave set up in the tube. Mark with the letter N the position of any nodes on the stationary wave. The frequency of the fork is attohertz, and the difference in the height of the water level for the two versions of the liquid solution is 32.24 centimeter. Calculate the speed of the sound in the tube. In the tube. This part you can do it very simply, because this much is lambda by 2. So you just label this as lambda by 2 equals 32.4. You calculate the lambda, the frequency is given, then you calculate the v equals to f lambda, the speed of the wave in meter per second. Do the necessary unit conversion. You shouldn't mess it up. How to draw this thing properly, I'm gonna show you a little bit of help for this one. How to draw this part. As I've shown you in the lectures as well, that the easier way to draw this kind of waves is always first divide the segments in the number of pieces that we're going to require. So we do understand we're going to have a stationary wave produced over here, where the open end should be a node and the bottom should be antinode. So there should be lambda by 4, or this much shape 3 times. This whole length is supposed to be 3 lambda by 4. So what I'm going to do, I'm going to use my ruler, or you can, if you don't want to use a ruler, you can essentially eyeball it, because this is pretty simple. You can just hold your ruler along this line. So just take your ruler and hold your ruler along this line, something like this. I'm not gonna keep it over here, just showing you, and draw a certain point right over here. So let me erase that, because I don't want that to cover the figure. So I'm gonna mark one point right over here, which should be at the same level, because this part would remain unchanged. And you can divide these divide the remaining part into 2 segments. So now you have approximately 3 segments where you are supposed to draw the shape of the stationary wave. So that part you have to practice and you can get better with bigger amount of practice. So I'm going to give it a bit of a try. Let's say this is my one thing, and then this part should continue to give us antinode. We must touch in the side of the air column, and it goes to make a node over here. So this was my point. So I'm gonna fill the other side, draw the other side, and from here it should go around like this. It should go down further like that. And this point is to be labeled as n, so you can either use a line and label it n, or you can simply write n over here. That also works, because it is important that you label this n with a letter, because the question demanded that mark with the letter n the position of any nodes on the stationary wave. So you could mark it over at this point. This is a node, you can mark it over here, or if you want to mark exactly over here, you can also mark it right over here. But you do make this dot visible, so the examiner knows that what you're trying to show them. That's pretty much it for the drawing. And for the calculation, I think you can do this. If you can't, I might help you later on, because the calculation I find is to be pretty simple.
Sir,
Yes.
no matter what the length of the tube, will one end be an antinode and another one will be a node always, or
For a one enclosed tube, yes. That's how one enclosed tubes behave. The entry point for the wave is always an antinode, and the reflection surface is always a node. So this is a one enclosed tube, because this water surface is working as a vibration, as a reflector. If it was a both an open pipe, then would have a different shape, where there should
okay,
be
sir.
two antinodes on the two sides. It depends upon what are you working with. Are you working with one end open tube, or are you working with both end open tube? That's the important thing which makes the difference. Mucho.
Okay, sir. Yes, sir.
Beautiful. So, okay. The length of the column in the air in tube in figure 6.1 is 15.7 centimeters. So here comes the question about the end correction. So let's take a good look. The length of the column of the air in tube in figure 6.1 is 15.7 centimeters. So now they are telling us that this amount of air column is 15.7 centimeter. And if you do the division, you'll find that this is not exactly half of that. Half of this is 16.2. So I mean, so half of this is 16.2, whereas the length of the air column over here is 15.7. So you do understand that the antinode was produced the difference amount above. The question says that suggest where the antinode of the stationary wave was produced in figure 1 is likely to be found. This is a pretty simple question, so I might as well show you the calculation for this. They are asking us that where the antinode is most likely to be found. Might as well increase the space a little bit, or I could write on the right side as well. And later we get rid of the whole thing together. So what I want you to see is that for this much gap, this was 32.4. So this was supposed to be lambda by 4. This is where, how much we have covered for one full lambda. Sorry, one lambda by so one lambda by 2. So there are two lambda by 4s over here. So this much space by the question, you don't have to label on the question. I'm just labeling this to make sense with you. This is 15.7 centimeter. Logic tells us that this halfway distance should be 16.2 centimeter, and obviously the lower half is also 16.2 centimeter, which will be exactly half of that. I mean, they are equal in lengths. So we do know that we have a bit of an end error over here because of the position of that uniform, that we cannot hold exactly on the opening of the air column, because that would stop the vibration by means of collision. So we have to hold it somewhat slightly above the wind pipe or wind tunnel or wind section. And by comparing, you should be able to see that if we do a bit of a difference between these two numbers, you can calculate exactly how far above this was produced. So that difference is what you are supposed to do. So because there are two marks over here, what I want you to do is just show the examiner that you know your thing. So let's say 32.4 divided by 2 equals to 16.2 centimeter. And you can also show that 60.2 minus 15.7. How much this gives you? 0.5 centimeter? 72, yes. 0.5 centimeter. So show them this calculation by one line, and then you can write antinode is 0.5 centimeter above the open end of the tube. I'm using the simple one term tube. If you really want to label this as a, what is this thing called? Burette. This is a burette, right? This device that you can see don't we call this a burette?
Yes.
Yes, sir.
So you don't have to mention burette because it just says long tube, so you use long tube. It looks like a tube, it is a tube. Beautiful. So I'm just using that. Do you understand this part of the calculation, that where did the half come from and why did I subtract this thing? If I calculate it over clearly. Okay, I believe so. And then let's go for the next question. Yeah, number 3 is very interesting one. This is a very basic way, or to be honest, quite an effective way to produce stationary wave in a visible way. Actually, whenever I was going through the lecture, I actually showed you the mechanism by which you can make a visible stationary wave on a flat surface where there was vibration made by a certain source or by a violin. What is this called? Violin bow to a metal surface where some tiny sand or dust particles could arrange themselves in very beautiful geometric shape. That was the stationary wave produced in a plane surface. This is actually a case for stationary wave produced in along the length of the tube. The idea is very simple. Initially, the question just doesn't say, have a look. The glass tube closed at one end has fine dust sprinkled along its length. So initially, the height of this dust around the entire tube was uniform. So there was uniform amount of uniform thickness of the fine dust was sprinkled around the whole length. A source of sound is placed near the open end of the tube, as shown in figure 5.1. The frequency of the sound is emitted by the source is varied, and at one frequency, the dust forms small heaps in the tube. So this will never. So we had to change the frequency of the source to come to such a sweet spot, so that its wavelength shape would be such that it would be able to produce stationary wave within this length. You should understand and you should remember that we cannot produce stationary wave at arbitrary lengths. The stationary waves are already produced so that it can fulfill the requirement of the medium that we're using. For example, in this case, the medium is the open-end aired column, which means we need to fulfill the requirement that one end should be a node, which is the reflection side. In this case, is the right side or the closed end of the tube, the bottom of the tube, and the open end should always be an antinode. So this, the requirement for stationary wave for this air column is that we need to have an antinode in the left side, and we're gonna always have a node on the right side. And whenever that thing perfectly matches with any of our with any convenient number, for example, you can have lambda by 4, 3 lambda by 4, 5 lambda by 4, 6 lambda by 4, sorry, not 6 lambda by 4, 7 lambda by 4, because we can only have odd multiples of lambda by 4. That's what we have seen in our earlier lectures. So whenever the frequency of the sound source matches to give us such a wavelength, which somehow matches with any of those required fractions, only then are we going to have the stationary wave. That's why it is required that we must change the frequency of the source, which enable us to get this shape for certain frequencies. So that's one part. Now the question says, explain by reference to the properties of stationary waves why heaps of dust are formed. So whenever, this is a 3 mark over here, so we have to say, so far I can remember, we have to say, talk about a little bit about how the stationary waves actually get formed, a little bit, because it says explain by reference to the properties of stationary wave. And then we have to talk about the nodes and the antinodes and how the movement of those air particles are causing those heaps. So if I was writing this question, I might as well be writing like this, that the two sound waves, one coming from the sound source and another one reflecting of the right end of the tube, merges with each other, or you can write superposed onto each other to produce a stationary wave within the tube. So I'm going to say these two, mention these two waves for one coming from the source and another one reflected off from the right end. So these two are so I'm going to mention these two waves which are producing the stationary waves over here. First sentence. The second sentence I'm going to write, at positions of antinode where we have the maximum amplitude, air particles are moving vigorously and they move the fine dust particles to the nearest nodes where the movement of the air particles are very small / 0, and the dust particles can rest at those positions. So I have shown you in one of those animations that how does the stationary particles move. You should remember that they essentially move in opposite directions from node to node. The actual way, to give you a better visualization for what is happening over here, I can try to draw the possible shape of node and antinode within this tube. The way it works for this tube, I might not as well fill up the whole tube, is that above each of these clean point where we don't have any dust, we'll have one antinode. Above each of these heaps, we should have one node. Because within this part, the air particles are vibrating really fast and they are sweeping, basically jharu dawa, or they are sweeping those dust particles, fine dust particles, to the positions where they can be stationary or they are able to become stationary. So if I try to show you the shape of this stationary wave, it might as well be node, antinode, and then node, antinode, and then node and antinode, like that. So this is the actual shape of the stationary wave which is being produced over here. So important for you to understand that the top of every peak, we're gonna have one node, and between every two nodes, we will have one antinode. So this is the structure that we have. Before we go for the next question, I'd like to see how the examiners actually explain this question. I did not open the examiner's report mark scheme, so let's have a look at that one so that we can have a better idea of how they expect it. This is question number 3B. So let's have a look at that. Question number 3B says, at dissociation of antinodes where there are no heaps, waves at maximum amplitude of vibration. Okay. At dissociation of nodes where there are heaps, amplitude of vibration is 0 or minimum, dust is pushed or settles as dissociation nodes. I think in my description I covered these 3 points, but I also mentioned one additional point. I told the examiner what are the 2 waves that was actually here. So, okay, works. Do you understand the meaning of this mark scheme, everyone? Does this make sense? If you have any question, might as well take the question, but let's look at the examiner's report over here. Frequently, the candidates wrote about the length of, this is actually very dark mark scheme. Might want to change. Okay. Frequently, candidates wrote at length about the formation of a stationary wave rather than its properties. It appeared that from a significant portion of answers, some candidates had not seen this effect demonstrated and were quite unaware of the fact that the dust would settle at nodes. Anyway, so yeah, works for me. I hope it works for you, since none of you are responding to any about any questions. I
Sir, I got the
sure.
examiner's report.
Language support. If you have any question, you ask me. I'll help. Both the mark scheme and the examiner's report. Read both of those.
স্যার হিপস দিয়ে কি বোঝার চেষ্টা করছেন?
Try to understand. There are uniform layering of a. Let me. Let's see if we can find out an animation, or maybe even better, if you find a simulation for dust particle. Disregard that. I think my brother is trying to call my mom in my cell phone, so forget about that. Dust particle, stationary wave. Amma phone dharo. Do we have a video for this? Would have been better if we can find. for this. Okay, there is a YouTube video for this one. This video is unavailable. Volume down. Why is that? Okay, maybe the uploader deleted this video. I don't know why. This might have been a good visual demonstration, but if it's not available, it's not available. Acha, if I found out a better video later on somewhere in my research, I might as well share this. But let me explain this thing. What is happening for those who are having a bit of a difficult funny to be difficult to understand. Let's say this is the tube. Consider that this is the tube, and within this tube we have produced a stationary wave. Now, in positions where the stationary waves have produced, in the positions of anodes, antinodes, we're going to have a really large amplitude. Let's say on the opening side. Then the amplitude is going to slowly become smaller, 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 and there will be a node. So node is the location where the air particles are not moving, or their movement is really small. Exactly at the node position, the amplitude is 0. Close to the node position, the amplitude is pretty small. So which means here the air particles are not going to disturb the dust particles too much. So these locations are going to allow the dust particle to settle. They're going to keep the dust particle undisturbed. Whereas at this position, the air particles are moving really fast. So they're going to move the dust particles with high amount of vibration, which will make, let's say initially we had this much of a dust particle accumulation over here, maybe straight line, better, rectangle, better. So let's say initially we had this much dust particle which was placed at the bottom of this thing, and eventually when the stationary will be produced, these dust particles are going to move from the antinode positions because of the motion of the air particles. So the air particles are going to basically vibrate them out and left and right, and because they can actually come in a more stable conditions right up over here, these dust particles are going to move to those positions. So the new position that you should expect, that on the antinode position, close to the antinode positions where the amplitude of vibration of the air particles are pretty fast or pretty large, the dust particles cannot settle there because they're going to be moved, and they're going to produce heaps of dust particles close to the node position, because here the particles can actually come to stationary. So this part is going to be empty, and then in the next node position we're going to have another heap, and obviously because the node is always produced on the back end, so we're going to have half of a heap at the last end. So that's the reason, because the moving air particles actually pushing the dust particles on the two extreme node positions. বুঝাচ্ছে?
Yes, sir.
Yes, sir.
So that's what is happening. So পরের কোশ্চেনটা actually আমাদের জন্য বেশ interesting, because we have to do some count. Have a look at the next question. It says that the distance between 6 heaps, as shown in figure 6.1, is 39.0 centimeter. Calculate the speed of sound in the tube. So take a good look at this figure. These 6 heaps over here, they have a total of 39 centimeter. Now you should remember, above each of this heap we have node, and each of the empty space represent an antinode. So you can very easily count how many loops does it contain. So here to here, 1 loop, 2 loop, 3 loops, 4 loops, and 5 loops. So within this part we have 5 loops, which means 5 lambda by 2. So the way I'm going to attempt this calculation, which I believe I have over here, I don't have it over here, so I can actually try this thing right on the right side. Let's get rid of this earlier calculation. Forget about that. Choosing black. So I can go that 5 lambda by 2 equals to 39.0 centimeter So that's how I'm going to solve the problem in the actual question. Therefore, lambda equals to something, so you can calculate this out. The frequency of the wave was already given, so then you calculate v equals to f lambda, you place those values, calculate these up, and you get your answer. So that should give you somewhat like this, which they have calculated over here. So 2.5 lambda, so they have given 2.5 lambda, I have written 5 by 2 lambda, which basically works, because I personally like to calculate in terms of the lambda by 2, which gives us the number of loops, fraction in terms of fraction of loops. That's how I personally like it. I find it easier to work with. But pretty much you're gonna get the same answer. So you're gonna get 334. This is a 3SF answer. If someone wants to give the answer in 2SF, they're allowed to give this answer as 330, but not 340. If someone gives 340, they're gonna lose this mark. So that's that. If we have a look at the examiner's report, only a minority realized that the distance would be 2.5 lambda. Many thought that it would be either 5 lambda or 6 lambda. This only shows that the students were not capable or to understand how the stationary works or the heat production works. Any questions so far? বুঝা গেছে কিনা? Are you clear on this? Yes, sir. আচ্ছা এটা গেল। আচ্ছা এটা একটা খুব ইম্পর্টেন্ট কোশ্চেন। স্টেশনারি ওয়েভের এই কোশ্চেনটা খুব রিপিটেডলি আমাদের কোশ্চেন পেপারে আসে। You are seeing it from the first time, and then later this exact question will be coming up in a lot of other places. We might take this question a bit seriously because it's a repeated question, so you might as well learn this. The wave in the tube is stationary wave. Explained by reference to the formation of a stationary wave. What is meant by speed calculated in B2? Whenever you are trying to mention the formation of a stationary wave, there are a couple of things that you need to mention. What are the two individual progressive waves which are causing the stationary waves, which produces nodes and antinodes, or you can say locations of maximum amplitude of air vibration and zero amplitude of air vibration, which are antinodes and nodes respectively. The speed that we've calculated is practically the speed of one of those progressive waves. What I'm trying to mean is that through this tube, we're going to have two opposite going waves passing through each other. Let's say one wave is going to produce from the sound source, which is the left to right, and another wave is going to be produced from the reflection, which is going to be traveling from right to left. These two individual progressive waves will merge into each other to give us the stationary wave behavior. So the speed that we are calculating is actually the speed of any of these two progressive waves, and these two progressive waves will have the same speed. So you can say any, or you can say each. But don't write both, because speed of both might actually mean a bit confusing. So you have to mention specifically that the speed that you've calculated belongs to either or any of or each of the progressive wave, individual progressive wave that is responsible to produce the stationary wave. If you look at the language for the mark scheme a little bit, so take a good look for the question. The mark scheme says stationary wave formed by interference or superposition or overlap of either waves traveling down the tube and its reflection, or you can write two waves of same type and frequency traveling in opposite direction. So you can essentially, as far the question says that this part is containing 2 marks. So the word interference, superposition, or overlap, this scores you 1 mark. And what are the two things that overlap or interfere? Mentioning that thing scores you the 2nd mark, which means you have to say that two waves either traveling down the tube and its reflection, which is the exclusive case for this experiment, or we can go for the generic version. Generic version means the typical normal word description. The two waves of same type and frequency traveling in opposite direction. This is the generically acceptable description for stationary waves of the two progressive waves. So this is the part. These 2 marks are for the in terms of the construction of the stationary wave. This part explained in reference to the formation of a stationary wave. This part is covered by these 2 marks, B1. Then they are specifying the speed is the speed of the incident or reflected wave. So any of those 2 waves. Each of the progressive wave move at this speed. If you go for a bit of an examination report, candidates are told to consider the formation of a stationary wave. There are some good answer descriptions, but many did not make it clear that the stationary wave is formed by superposition of the wave traveling down the tube and the wave reflected from the closed end. There were some answers that showed a lack of understanding of the situation. These included the speed of the wave and the speed at which the nodes are formed. So you cannot only mention the speed of the wave. You have to specify that this is the speed of one of the progressive waves, or either the incoming wave, or you can say it is the speed of the reflected wave. Any of those, you have to specify that because you have to understand one thing, that stationary wave, the name itself tells us that the speed of the wave is zero because we have equal amount of energy transferred in either direction. So there is no net energy flow. So if you say by name something is stationary and then calculate the speed out of that property, it cannot be the speed of the stationary wave. Rather, it is the speed of any of the progressive wave, any of the two progressive waves which are responsible to make the stationary wave. So to specify that very clearly. The next one is pretty simple. You can try to draw the 5. So did I tell you about the leading and the lagging part for two waves? Ever?
No, sir.
Okay.
No, sir.
So let me just show you a figure and then I'll go for the explanation. This is shown for voltage, but it is equally applicable for waves as well. For example, I think this is for AC circuit, because in AC circuit these informations are more uh, prominently used compared to waves. So one of the things that I would like you to understand, take from this information, then I'll tell you what is happening. This green wave is, let's say, this is a certain position of a wave. The one that is in our graph would be behind that is called the leading current. The one that would be on the right side would be said to be the lagging current. In this case, it says current, but for our decision to be wave. So what does this mean? What does this mean? So let me show you maybe by this figure. This will actually help me. Copy this image and try to explain. Control V. Now if I try transparent selection, maybe place it like that. Disregard the 180 writing. I'm trying to overlap them properly so that I can make sense with you. So you should be seeing that between these two waves there is a 90-degree deviation. We say this is a lagging wave and this is the leading wave. I'll tell you why this is happening. The leading wave is the wave that is produced from the source earlier. The lagging wave is the one which is produced from the source later. So the term leading and lagging is relevant with respect to the time instance at which those two waves are produced. So the reason we have a shape like this is that hold up just a second. Got it. Let's say we have two particles over here, or two sources. I'm saying those two particles as two sources. they are going to undergo some amount of vibration. Now, if these sources are coherent, that means their frequency would be constant and they would have a constant phase angle difference. Typically, the type of two sources for the double slit experiment or those kind of experiment that we use, they usually have zero phase difference, which means they both have the exact same phase, 0 degree, 0 degree, 2 degree, 2 degree, 4 degree, 4 degree, like that. So they move synchronously with each other. Let's consider a scenario where these two waves are not having a synchronized motion. Let's say this particle is going to move up and down up to this much. This is the mean position. Let me draw the second one a bit lower, the different color maybe, so I might as well delete that. So let's say the second source is green, located here, and let's say this is going to have an amplitude of going up and down by the exactly same amount. But so I can draw vertical lines, almost vertical lines. So let's say their amplitudes are going to be exactly equal, but their phases are not exactly the same. So for the sake of understanding, let's say that they're going to be vibrated from a single source that is placed right over here. So this is the primary source, which is going to be producing vibrations, which is going to spread out in all directions. Now this wave is going to reach a part of a wavefront earlier. This wave is going to get that same part of a wavelength a bit later, because the way I have drawn this figure is that I have tried to achieve that this length is a bit smaller and this length is a bit longer. So the same wave will reach here earlier and this will be reaching later. এই পার্টটা বুঝতেছো কিনা দেখো। Follow on. Using a primary source, I'm going to try to vibrate two different openings over here, or two different exclusive sources over here, or two different particles of the medium over here, who are going to be experiencing a bit of phase difference, because the same wave will not be reaching exactly at the same time to both of these waves. Let's assume that whenever any part of the wave that reaches over here, let's say this certain wave reaches over here, when this one's phase is at 0 degree, this one hasn't yet received that wave. Whenever this particle's movement has reached, let's say 90 degree means, let's say when this particle has moved to its crest, let's say only at that point this particle is reaching the 0 degree phase. Now 90 degree phase angle essentially means how much path difference. You should remember this thing, that lambda was relevant to 360 degree phase difference, and which was also relevant to t amount of time period. This is the golden relationship that we use for explaining the wave behavior. So if we have a 90 degree phase difference, which means the path difference is supposed to be lambda by 4. This essentially means the figure that I'm trying to propose you over here, that if this much length is, let's say, x, then this much length is supposed to be x plus lambda by 4. Why lambda by 4? Because this one is reaching the same wave 90 degree earlier. So when this wave particle is at 90 degree phase, this wave particle is just at 0. So from this point onwards, how would their wave look like? At this point of time, this is producing a wave which is producing a shape. So this particle is right over here. So if I try to draw the exact wave produced from this wave, at this instant this wave is right over here like this, drawing from the 90 degree, and this wave is only starting to start its behavior from 0 degree. So it's gonna give us a wave like that. So if you just try to see that if we now do the merge of these two waves, if we do the sum of these two waves in a single figure, this might as well give us a situation like this, which is gonna be somewhat, I might not as well draw this, show you over here. The merging of these two waves on a single piece of graph is gonna look like this. So the wave which received the information or the wavefront from the source earlier is the leading wave, because it is reaching to the crest position a bit earlier. And the one that received it a bit later, it is receiving a bit later. I think, is this actually 90 degree? I'm not sure this gap is actually 90 degree, because 90 degree was the perfectly swap হওয়ার কথা না? I think I messed it up. আচ্ছা 90 degree হচ্ছে two division, sorry. Let me cut this out, because since all of my discussion was about 90 degree, so let me recapture this thing and make it 90 degree for your understanding. I'll take questions in a while. If you have questions, just bear them in your mind I'll take them just in a while. So 90-degree path difference would be actually this much. This would be a better situation. So this is the situation where we have merged, we have drawn both of these two waves on a single piece of graph. And what this shows that when this top source, let's say brown source, this was reaching the crest right up over here, at this position, at this time instance, this second wave is only starting to vibrate from its equilibrium position. By the time this has come down to its equilibrium, this is only reached up to its top. So you see that there is a 90-degree phase shift between these two particles. But the one that we are calling the leading source is actually leading in terms of it received the original wave from the primary source, which is this one, uh, it received that information earlier, and this source received the information earlier, hence it is the leading source. It goes that phase earlier, and this source received the information a bit later. That's why this is the lagging source. Whenever we'll place them on the same piece of graph, the lagging source sorry, would always appear on the right side of the leading source. So in terms of graph view, it would appear that this is forward compared to this, but that's not true. It appears to be forward onto this thing because it is slightly late. This wave is reaching the exact same phase 90 degree earlier compared to this. So we can say that this wave is 90 degree delayed compared to this wave. So this is our lagging wave, and the one that appears to be behind is our leading wave. এই জিনিসটাকে বোঝা গেছে যে কেন সামনে apparently on the right side one is the lagging and the why apparently on the left side is the leading. From this discussion, can we make sense of this figure? Anyone? If you have questions, please ask me. I'll take questions now. Hello.
স্যার থিটা অ্যাঙ্গেলটা একটু আরেকবার বুঝাতে পারবেন?
Yes, I have intentionally placed the primary source. These particles that I have shown as our particles over here, you might as well consider this thing as a typical mechanism that we have described earlier. For example, here we have a light source, okay, and there we have a single slit, and there we have the double slit. Let's say here we have the double slit. Here we have the double slit. Now let's say I have placed those two double slits in such a way that the top one is a bit closer to the source and the bottom one is a bit further away from the source, in such a way that the distance between these two sources from this first slit is lambda by 4. So let's say if this pathway was x, whatever that is, this pathway is x plus lambda by 4, which means whenever this wave would receive 0 degree, or the first wave coming from this source, that wave would still be somewhat behind reaching this source. Within the time this source would have gone from 0 degree to 90 degree, that's when the second source is going to receive the 0 degree wave. So it is only starting when this wave has already completed quarter of its cycle. So this one, in terms of the same instance of time, this wave would always have a 90 degree ahead compared to this source, because this is receiving the waves earlier. So this is the leading source, this is the lagging source, which if we plot on a single piece of graph can appear like this.
ওকে স্যার।
বুঝা গেছে এখন?
জি স্যার।
Beautiful. So it actually our মাঝে confusion হয়. That's why I was taking a bit of a time to think about the drawing that I was about to do, and then I started because I didn't want to confuse you kids. But if you don't want to remember it in this format, I mean, it's not essential. তোমাদের কখনো এইভাবে এত ডিটেইলসে এক্সপ্লেইন করতে বলবে না. All that you have to remember that the wave that appears on the right side is the lagging one. The wave that appears on the left side is the leading one. If you can remember only this much, you're good to go. You don't have to know more than that. I just give you a bit of an explanation to convince you that why this is the leading one and why this is the lagging one. Why apparently on the right one is the lagging one and why apparently on the left is the leading one, because it's not essentially about how the waves look like. It's about which wave was made by that or experienced by that wave at a certain point of time. That's what this is about. So why did I tell you this? Because here in this question, we have to draw a wave on this figure. So we might as well look at this thing. A second transverse wave T2 of amplitude A has the same waveform as T1 but lags behind T1 by phase angle of 60 degree. Important information. A second wave lags behind this wave by a phase angle of 60 degree. The two waves T1 and T2 pass through the same point. First they're saying on figure 5.1, draw the variation with time t of the displacement x of the point of in wave T2. So first of all, we are asked to draw the wave T2 over here. So might as well copy this picture and try to draw this. I'm definitely gonna use copy paste, which suppose they're saying. So we are asked to draw a wave that lags behind this wave by 60 degree. Now lagging means we have to replace all of the crests and all of the troughs and all the entire wave has to be shifted to the right by relevant amount of 60 degree equivalent of phase angle. Now this horizontal scale you can see over here, this is actually timing axis, and you don't have to bother about that as long as you can count the divisions. So remember that. Let me write this first for you. So the way we know this thing, that 1 lambda is relevant to 360 degree is relevant to 1 time period, which for this question is relevant to how many divisions? 10, 20, 30 divisions. এটু বন্ধু বুঝতেছ না বলবান দেখো ঠিক আছে?
Yes, sir.
So if we're now trying to convert this into 60 degree, go for direct unitary method. For 60 degree, this will be how many divisions? Here it is 1/6. This will be 5 division. Which means now we are going to try to shift the entire, the new wave should be actually 5 division shifted to the right compared to the given wave. Because we are trying to draw a wave that is lagging behind, which means this wave should exist on the right side. If the question said the draw a wave that is leading, then we should try to shift all the particles to the left. So how are we going to do this? First, I'm going to show you the point location, and then I'm going to show you how it is easier to draw. So this point is going to move by 5 divisions. Let me draw it red, makes it easier to see. So this is going to be one of our point. This moves up over here. This is going to be one of our point, and this point moves up to the right. So this is going to be one of our point. This is going to move over here. So I'm practically moving all the relevant points by 5 divisions. So this gives me actually 1 half cycle. So I might as well try to draw freehand, but because I can, I'm going to do a bit of a cheat and copy from here. So let's try see if I can do this successfully. Let's start. Okay, let's start copying from cleaner version. Yes, copying this much should do. And I'm going to rub off this 1, 2, 3, 4 writing, because I don't want these to this thing. I can actually rub the whole graph, but I don't think that's essential. Should I try that? So that pretty much, I believe, helps me, and I'm gonna color this with red. So let's see if that works out. Nope, I cannot color this with red. So let's say this is the wave that I have, and I'm going to shift this. I'm going to place this onto the graph in appropriate place so that I can have it moved around. So let's do this. I'm going to copy this up. So my new wave is going to start from here, and this is how it's going to look like. Take a good look, kids. Not the very perfect graph. Why is it so difficult to do? Well, I should be able to align it perfectly because I just copy paste it. Yes, this is the perfect shape of the new graph, how it's going to look like. All the points shifted by 5 division to the right, which respond to 60 degree. Now you might wonder, sir, what's going to happen for the left side? Are we going to keep it empty? No, we're not going to keep it empty. But let me just complete this graph up to the right side by copy pasting this figure. It's the same figure. You have to copy this. You have to complete this figure up to the point they have shown. So on the vertical axis, your endpoint, and the question's endpoint should be exactly same. So might as well do it up to here. So this is the first part that we're saying, and then we have to fill it up this part as well. Now, drawing this left part is actually quite simple. You just have to use a little bit of part of your brain. You have to understand that the waves are always symmetric about its crest or the trough points, any of the 2 points. So you can see over here, have a look, that on the right side from the crest point, this went down, vertically down by 5 division with a horizontal spacing of 5 division. On the left, you still have 5 divisions as well. So it is only natural that this should be completed like that. You would not be able to draw this much of a beautiful graph, but as long as you can plot out all the points first, and then you draw a smooth graph as best as you can, you will be practically covered. But do you understand what this means? How this graph came into existence by the 60 degree lagging? We might as well label this as T2. এটা কি বুঝা গেছে ড্রয়িং এর প্রসেসটা সবার?
এক্সিস এর ওই পাশে শো করা লাগবে না?
না, এক্সিস লেফটে শো করা লাগবে না. You have to essentially draw your graph for the same horizontal axis length that the quotient gives you. Because the quotient gave us from t equals to 0 all the way up to this much divisions, our graph has to be that much bigger only as well. Axis left show kora lagbe na, because well, as far as the time axis goes, this is the t equals to 0. So if t equals to 0 is already given, it means this is exactly where the vibration starts. So before this time frame, there was no vibration. So the answer to your question is no. You don't have to draw it on the left side of the axis. So if we have a go for the next part of the question, have a look over here. It says, on figure 5.2, draw the vibration diagram. This one x of the point in wave T2. So we label this, drew it, and also labeled it. Explain what is meant by principle of superposition of 2 waves. Explain what is meant by the principle of superposition of 2 waves. I did not teach you this principle by this exact heading. So this is something that you might have to churn out from your understanding. What do you understand by the principle of superposition?
So like chord theory ta.
Yes. Explain what is meant, which means you can use your own words. It doesn't have to be some rot taken memorized words, set of words.
Sir, two particles with different wavelength, velocity and momentum may share, entanglement both in superposition, the particles momentum and velocity is probability of either and is not all the more certain.
That's, I think you just mentioned the uncertainty principle.
Oh, sorry, sir. Mixed square fallacy. Sorry, sir.
It's all right. No big deal. Happens. So this is asking us about the superposition of 2 waves. Just without bugging your head too much, just think about what essentially do we mean by the superposition of 2 waves. The idea is very simple. If in a specific location of, or if two waves meet with each other at the same point at the same time, because those 2 waves are about to get merged, so they have to meet each other at the same point of time at the same location. So if 2 waves of same frequency meet at the same point at the same time, they're going to combinedly affect the displacement of the medium particle together. If they meet with the same phase, they'll make constitutive interference. If they meet in the opposite phase, they'll do destructive interference. This is the key part that you know. 2 waves merging onto each other, meeting with similar phase, or same phase, you add up the displacements to get a much bigger amplitude, or if they are made in the opposite phase, you get a much smaller amplitude. That's basically what you have learned. That's basically the layman's version of what you have learned for the idea of principal superposition. Now, just to be sure, let's have a look at the mark scheme. That what is the post word set that the examiners look from you? Question number 5. Take a look. So what do we have? Take this out. Words must be in the same
Position
place
at the
at the
contour.
same time.
Yes, sir.
This is the important bit. This is a very important bit because we are maintaining that the two waves should meet with each other. The two waves must meet with each other. This is important. In that case, the resultant displacement is equal to the sum of the individual displacements. That's basically it. If we have a look at the examiner's reaction, have a look. Most candidates did appear to have some understanding of the coherence. However, an appreciable portion of either did not establish that the waves must coincide at the same point or made reference to the amplitude rather than displacement. Have a look. In this case, they have mentioned that it is not about the amplitude, it is about the displacement. This is actually quite important. They have underlined that word, that why do we have to stick to the word displacement and not the word amplitude? Try to understand, kids. Whenever we do the combined figure of the two things, for example, the figure that apparently look like this, where it is, hold up. Let's talk about this one. Whenever we discuss this figure, this is also in your my Kandel book. We have this similar figure as well. You have to understand that exactly at this position we added all this because they are both in the same phase. We only added the amplitudes right over here. We could get the amplitudes exactly over here. But if you consider this scenario, here we had the merge of opposite phases and similar phases both. So we didn't necessarily add up those amplitudes. For example, here the individual amplitude of the dotted wave is located here. Individual amplitude of the dashed wave is located over here. We could not add those amplitudes because they are not in the same time. But we could very well add their individual displacements. For example, at this location, both the waves made us equal amount of displacement. So this green wave is basically double the distance of the cross point. So how much is over here? If this part is, let's say, x, then the total displacement for the green wave was 2x. So we added the individual displacement of both the waves to get the resultant displacement of the total outcoming behavior. So we didn't essentially add the amplitude because amplitudes are applicable for progressive wave. Amplitude is applicable for only a few points of that wave at the crest positions and the trough positions. What about all the other points in between? Don't they have any movement? They do. Their movements is what we call the displacement. Only the particles located at a crest position or the trough position are at the amplitude displacement. All the other particles at some other displacement. So in the process of finding out the resultant wave, we essentially add up their displacements, not the amplitudes. Typically, to make the drawing process easier, sometimes what we do, make the drawing process easier, we only locate the points where the sum of the amplitudes, the overall crest points and the overall trough points is some of the points that we usually locate, and then we can draw the wave. That's because that is easier to draw. But that doesn't mean all the points in between did not essentially undergo any calculation. All of the points in between underwent some sort of calculation, and that is basically the addition or of all the displacements, or the sum of all the displacements. Now, displacement itself is vector term. So whenever we say sum of the displacements, the subtraction or addition is inherently within the description. That if you have both the displacement in the same direction, you actually add them. If they are in the opposite direction, you actually subtract them because displacement itself is a vector term. So does it make sense?
Yes, sir.
জি স্যার
আচ্ছা, এখানে আমাদের একটা জিনিস বলছে যে for time t equals to 1.07 is to get 5.1 to determine in terms of a the displacement due to the water wave t1 ln, t2 ln, Resultant displacement. Okay. At 1 second, let's have a look at our graph. This is a 1 second mark, and A was labeled as the amplitude. So for especially for T1 wave, which is a given wave, what is the individual displacement for wave T1? How much would you define this displacement to be?
Half of the amplitude.
Yes, so displacement should be come as a vector quantity, so it should have plus or minus. Does this displacement, is this displacement on the negative axis or the positive axis?
Positive y
No. This one, the drawn given wave. This one is currently having a displacement below the horizontal axis. So the displacement of this particle is actually minus a by 2. বুঝছো কেন?
Oh, হ্যাঁ.
ঠিক আছে? Similarly, the displacement for the our drawn wave, which was T2, this is supposed to be plus a by 2, and you have to preferably give the plus and minus both of these signs, the plus as well, because we are dealing with displacement, so you don't want to mess up the examiner in any way. Joshin, তুমি আর মামুন কোথায় গেছিলা? কোন যাচ্ছেন? That. So if you have a look at the mark scheme, I think it would agree with us, I hope. You see, they gave minus half a, and then they give plus half a. For the plus half a, they are allowing ECF. Allowing ECF means, have a look, there is no logical way you should mess up this value, because this is a value that was already printed in your graph. But there is all possibility the graph that you have drawn for 60-degree displacement of lagging, which this is supposed to be the correct graph, you might actually have messed it up. So if you have messed it up, you might get a different value compared to this one. This is supposed to be the correct value for a correct graph, but if you have drawn a wrong graph, you might as well read off a wrong value. That's why allow ECF is given, which means if the students have already drawn a wrong graph and they pick up a wrong value of displacement from that wrong graph and mention that value, and the students should get that mark. As long as their answer is perfectly agreeable with their drawing, they will get this mark. And this thing is supposed to be the sum of these two. So if they did not write halfway over here, they wrote something else, and this answer is practically the numerical sum of these two things, and then they should get this mark as well. So this was a bit generous on the examiner's part, so that they have allowed ECF for both of these questions. Have a look at the examiner's report. Although a minority did not appear to understand what was expected, the majority did read off values from the graph and then gave a resultant displacement consistent with their values. Weaker candidates frequently ignored whether the displacement was positive or negative. Pretty much what I said. So I hope that makes sense. Then we have some other question. These are simple. You see, that same question is popping up again. By reference to the formation of the stationary wave on the string, explain what is meant by the speed calculated in B. Exactly same question, 3 marks. So this is a repeated question. Gotta be careful about those. So I have two individual waves which are gonna merge onto each other, which don't have the exact same amplitude. Beautiful. This one has a division of 10 division or 2. This one has a division of 15 division, or you can say minus 3 or 3 division of amplitude. 3 value 3 into the minus 4 centimeter amplitude. You can try this out. These ones as well. Here you have to draw a certain wave. I'm gonna solve this question for you for a bit of a understanding. This is actually a pretty simple question. Let's have a look at this one. A student studying the water wave in which all the wavefronts are parallel to one another. The vibration t time of the distance x of a particular particle in the wave is shown in figure 5.1. So this is the wave. This is the graph of displacement of a single particle with respect to time. So as we're seeing that over time, the displacement is remaining the same. So the source is vibrating at some distance. The person is observing a certain particle in the pathway of the wave, and as the displacement of that particle is recorded or plotted with respect to time, we can see we have an uniform graph. Pretty normal, but important information is over here. That over here you can see that there is a decrease of amplitude, because this is not x versus time anymore. This is x versus d, which means this is the actual shape. Answer. Thank you. This is the actual shape. This is the actual shape of the wave on the water surface. So as we are going further from the source, energy is getting spread out onto much bigger number of water particles. So we are slowly losing amplitude, which is the typical common experience that we have. So if you observe one single particle over a distance of time, over the duration of a time, that particle is always going to have the same amplitude, which is obvious because we are observing one particle over and plotting its displacement over time. So that will have the same displacement over the duration of time. But if you observe all the particles over the distance from the source, then as you get further from the source, naturally speaking, the wave will lose energy. That's what is called damping, which is essentially, we don't have to know this word for your AS level, but this one over here. The part that is interesting for me is this one, that this figure 5.1, 5.2 whether the wave is losing power as it moves, whether the wave is losing power as it is moving away from the source. You have to write this answer in your own words. I'm interested in this ratio. Determine the ratio for the intensity of the wave at source divided by intensity of the wave at 6 centimeter from the source. Now, they are asking us to calculate the ratio of intensities, which in its core is actually pretty simple. We cannot exactly measure the exact value of intensity because we do not know how to calculate this. Let me tell you what I mean. What we do understand that for the equation of intensity and amplitude relevance, we know that I is proportional to amplitude squared. If you want to calculate the absolute intensity of a certain point, you need to know this value of constant value k, which is not given to us. So we cannot essentially calculate the actual intensity of a certain point. However, finding out the ratio is actually not a big deal, because if you have two different intensities, let's say I1 equals to k into A1 square, and then I2 equals to k into A2 square, and if we divide these two equations, what we get is I1 by I2 equals to A1 squared divided by A2 squared. Your unknown constant actually crosses out. So that's what we can do. This is essentially what we're going to do for this graph. The question says that we're going to try to calculate the intensity ratio at source divided by 6 centimeter from the source. So have a look. What is the displacement exactly at the source? This is actually 2 millimeter. And at 6 centimeter, how much would you define as this displacement? What is the amplitude at this point?
1.2 millimeters.
This is actually
1.1.
I think it is
1.1.
I think it's 1.1. বুঝছো যেটা কেন 1.1 বলবান দেখো রিড অফ করো because
Yes, sir. মাঝখানে।
ডিভিশন হচ্ছে 1 হ্যাঁ 0 তাহলে এক ডিভিশন 0.2 এটা তো হাফ ডিভিশন তাহলে এটা হচ্ছে 1.1 so simply to find out this ratio all that we have to do is 2 squared divided by 1.1 squared and whatever number you get that's basically your answer. So ratio বের করার জন্য আমাদের absolute value লাগবে না because the constant will be cut off from both sides, so you can simply calculate this ratio. এখন এটা আমরা এইভাবে করতে পারি. I think that's pretty much it. Why did they give 3 mark into this answer? I don't see the logic for 3 mark. What is so complicated that this question deserves 3 marks? This is question number 12C2. Let's have a look at this mark scheme and we'll call it a day. C2. Intensity is proportional to amplitude square. Ratio is 2.0 square divided by 1.1 square, 3.3. Okay. I don't mind. So, yeah. You have to mention this relationship first at some part of your question, and then directly go for the ratio calculation by the square of the amplitudes. Works for me. The well-prepared candidates scored full credit. However, some candidates misread the amplitude of the graph at 6.0 centimeter. Others did not work out a final value but left their answers as a ratio of the two numbers, and so were not awarded credit. So you see, they are not expecting you to give for you to give a fraction value. They're expecting you to give a decimal value. So always stick to decimal values, which I have been telling you from all levels, that always stick to decimal values, no fractions allowed. So the weaker candidates did not use the relation between the intensity and amplitude squared. So yeah, this is actually a pretty standard examination report. It deals with the typical problems that we have had. I hope this makes sense to everyone. Is this clear to all of us? This calculation process.
Yes, sir.
Yes. You have all the MCQ papers. You have all the P2 and the examination report as well. Start working on those. On the next class, I'll be starting with the P1 discussion of the Waves chapter. So I'll be first taking that one, and then I'm gonna finish the P1 of the supervision. So I'm gonna finish the two P1s first. First the waves. So if I show you in the, where is our Facebook chat window? So I don't know what is showing up. Okay, this was the one. So over here, I actually shared with you the two MCQs over here. This is 7. I don't know why this is also booked over as 7. This is supposed to be 8. Anyway, my bad. This is supposed to be 8 because I have labeled the supervision chapter as 8. Here it is coming up at 0. Achha. The numbers are a bit odd, but inside the numbers are all right. So I'm gonna first taking up these two MCQ papers. First the Waves one, and then the supervision MCQ papers. So I would like you to attend these questions. If you feel like printing them out, you can. If you don't feel like, don't bother. You'll have them in your hands pretty soon. Just try them from the PDF, do your calculation in your own copy, so you can respond to that discussion later on. And after I'm done with this, we'll be getting back to the P2 discussions once again. Kids, thank you very much. Good night.
স্যার আমার একটা কোয়েশ্চেন ছিল ডিফ্র্যাকশন গ্রেডিং থেকে
বলো।
আর ডিফ্র্যাকশন গ্রেডিং কনস্ট্যান্ট যেটা থাকে সেটা কি কখনো যে ওয়েভটা ইউজ করব ওইটার ওয়েভ লেন্থের সমান হতে পারে?
Well, it can be. I mean, there is all sorts of possibilities. The differential constant can be equal to the wavelength. It can be bigger or smaller depending upon what you want to use, the color of a light that you want to do experiment with, and the diffusion gradient that you can choose. It can be big or small. It can go in both ways, or it can be equal as well. But one thing that I would like to tell you is that how much of a good diffraction are we gonna have is actually dependent on whether the gap size is comparable with the wavelength. Diffusion gradient basically deals with the block plus gap. One block plus one gap gives you the diffusion gradient constant. So it is this thing that needs to be comparable with the wavelength. Did you get my point?
স্যার কিন্তু যদি ডিফ্র্যাকশন গ্রেডিং কনস্ট্যান্টটা ওয়েভলেন্থের সমান হয় তাহলে আপনি আগের দিন যে রাইট অ্যাঙ্গেল ট্রায়াঙ্গেল ফর্ম করে দেখেছিলেন না, তো এখন তো তাহলে ইকুইলেটারাল ট্রায়াঙ্গেল হয়ে যাবে, তাহলে রাইট অ্যাঙ্গেল ছাড়া ওই ফর্মুলা কি অ্যাপ্লিকেবল হবে?
Come again.
আগের দিন হচ্ছে একটা রাইট অ্যাঙ্গেল ফর্ম করে ইকুয়েশন দেখিয়েছিলেন না, ডি সাইন থিটা ইজ ইকুয়াল টু এন ল্যামডা।
Yes.
সো যদি ডিটা হচ্ছে ল্যামডার সমান হয় তাহলে ইকুইলেটারাল ট্রায়াঙ্গেল হয়ে যাবে, তাহলে তো এই ফর্মুলাটা কিভাবে কাজ করবে?
No. It can become an equilateral triangle, but your 90 degree will still be 90 degree. The other two sides would be equilateral. The other two sides will become equilateral. Let me show you what I mean. I think this is the one. The instant here's the deal. So let's say this is the scenario. If the d is equal to lambda, then this much was d.
Yes.
This is supposed to be a hypotenuse. Okay, actually you are actually making me think about this. I think that d is supposed to be always bigger than the lambda for this experiment to work. I did not I did not study about this, but this is a very good question because I can see that it's geometrically it's impossible for the d to be bigger than the lambda, because we're gonna have lambda as a portion of d over here, because n lambda is supposed to be d sine theta. Zarif, I'm gonna look into it and get back to you on the next class. But I answered your question wrong. What I told you, forget about that. I'll look into this and come to a better explanation. Okay, sir?
Okay, sir. Yes.
Thank you, kids. Good night.